Hi there, guys. Well, welcome back. We're about to do 4R and 4S, and we're talking about applications of differential calculus in this case, and in particular, we're talking about optimization for 4R and 4S, and then beyond that is kinematics, and well, we'll deal with that after we've done these two. So I'm going to roll the two things into one. In fact, what I'm going to do to start off with is I'm going to look at this question, which is talking about maximizing the volume of a box, and there's conditions for the dimensions of the box dependent on X. And then after that, we're going to have a look at the example in front of 4S, which is talking about maximizing profits when you've got costs and revenue functions on your graph, and you're thinking about how you're going to make a profit function as well and maximize that. So that's where we're going. Just before we do these questions, though, there's a nice investigation, of course. There's often these good investigations, but what I particularly want to say is that, in fact, there's two investigations here, is that these investigations are worth doing because they could lead to you doing an IA related to differentiation. To have some differentiation involved in an IA is quite common. To be using functions is quite common. What I'm talking about here is the internal assessment, or in other words, the coursework part of this course, which is worth 20% of the course. So that's going to be your own project. That's going to be, you're going to have to think about what kind of maths you're going to put in there. But a lot of people will do stuff which is related to functions, and differentiation is in the course. And obviously, those are a couple of big areas of the course, and you're going to hit a lot of ideas which are commensurate with the level of the course, right? So these questions which they come up with here, where they say, well, when mathematics is explained or applied to real life situations, its primary purpose is to investigate, explain, and solve real life problems. Okay, now they're talking about how to do modeling. And this is kind of a little process here of how to take you through an investigation, in fact, saying, draw diagrams, represent the problem visually, identify variables, identify constraints on the problem, translate the real life problem, carry the mathematics out which is necessary, reflect on the reasonableness of your results, apply your methods to other similar problems. Now, you keep going through that cycle, and that's going to lead to a good piece of coursework, a good IA. So you can see that applying your mathematics to real life problems is going to make a unique problem. So not just based sort of conceptually or in the sphere of pure mathematics. It's going to make a unique problem, and it's going to show off lots of your skills. So this is worth reading through and worth reflecting on when it comes to you making your IAs. Okay, enough said there. Let's have a look at the questions. So this is now example 34. Okay, so example 34, don't want that. And what I wanted to say beforehand, just before we do this, when we're talking about optimization, is maybe we're optimizing V and we're letting X vary. And I don't know, maybe the function comes out like this. And you say, well, I want to make V the largest possible. So there you go. You need the associated X value for this. Now, a lot of these optimization problems requires you changing your YX graph to the thing you're trying to optimize graph, or minimize. To optimize could be maximize or minimize, depending on what we're trying to do. But changing your Y to the thing that we're interested in maximizing or minimizing, and the variable which we're setting the problem up in. Now, if we're setting up in terms of two variables, that's going to be a bit problematic because we only know how to draw graphs here in terms of one variable. Okay, but likewise, this whole thing might be in terms of, let's think, we might be talking about optimizing our velocity. Use V again there, velocity in terms of time. Again, we're saying, well, here's our function. I can see that this point here is optimizing my velocity. So we're changing the variables in these cases, but essentially the same processes still apply. Okay, so let's see if I can just take this example here, which I can, it's still there. Those are X's at the bottom. Okay, so it says a piece of cardboard measuring 100 by 200 centimeters. So you've got 200 in this direction, and your 100 in this direction here. It is made into a box by cutting out small squares, each of which has a side length of x. Okay, so maybe you can think of this like a cereal box, for example. Okay, so it's looking a little bit like that. So that's kind of interesting. So we're talking about wrapping. It seems like we've got this and this and this. It seems like we've got three tops and bottoms, if you like. Okay, so maybe you need to chop a little bit out here as well. That's kind of interesting. Okay, well, it says cutting out small squares, each of which have a side length of x, as shown in the diagram. Okay, well, maybe they need a box to have two bits at the top which are going to open. Okay, so that's how they're defining the situation. Okay, and so then you've got a front and a front, and you've got four sides. You've got this side 4 times over. Okay, well, there's the diagram at least. So they're saying that this is how we're going to make it. So we're going to have to go with that. It says A is the length between the squares, and between the squares on the longer side of the cardboard, and B is the length between the sides on the shorter side of the cardboard. Fair enough. Okay. So find expressions for A and B in terms of x, and state the constraints on the lengths of x, A, and B. Okay, well, so there's some overlapping which is necessary according to the diagram of the net here. So we are going to have to go with that. We've got 100 and we've got 200 there. Let's find expressions for A and B. Well, B is obviously equal to 100 minus 2x, and hopefully you can see that A, where's A? So A, this length here, A is going to be equal to our 200 minus 3x. Okay, so let me just check that they've got that here as well. So yeah, they're saying A is equal to 200 minus 3x. Oh, yeah, not quite, is it? Because actually we've got a minus a from that as well. So we've got to minus another a from that. Okay, so that's our expression for a. And then we're going to need to, because, obviously we've got to minus that a there as well. So then we're going to need to simplify that. We'll take 100 minus 3x is actually equal to 2a, and then a is equal to 200 minus 3x over 2. Okay, now you can simplify that. Of course, you can split that into two fractions with 100 and minus 1.5x. Okay, so we can see that we got that. So yeah, although this is maybe not the most efficient net possible in order to create a box, we can see that they've got overlapping sides in order to make that box. For whatever reason, that's how they're defining it. Now, if you were going to make this, you might say, well, actually, my box is going to be, I could have my front and my back, and then the bottom and the top, and then the side and the side, and then I don't need another side and another side here. So I could do this, in fact, from a piece of card which doesn't have that extra bit on the bottom. Obviously, they want that extra bit on the bottom to sort of overlap with the top opening. Okay, I've said that a couple of times now, so let's not say it anymore. Okay, so we found expressions for these, and state the constraints on the lengths x, a, and b. Okay, so constraints for x. Okay, so we're thinking about what's our domain for x in a way. Well, we could see that x potentially, well, we could enlarge this x, this box here, until we get to the point that, that there's nothing left of b. So we can say that in fact the side length here is 100. So x has to be less than 50 there. Has to be less than 100 divided by 2. So that's one constraint on that side. And then you can probably see that if you could do that again on the other side, now it shows us that this length is longer. We don't necessarily know that that length is longer. Oh, yes, we do. We're told that A is longer. Yeah, told that A is longer. So we don't need to worry about the other one, okay? Because we could also think, well, what happens if A is actually shorter than B? You know, how are we going to set this one up from this side as well? And there you'd see that, in fact, 3x would have to be less than 200. But, when we divide this one through, we're going to get x is less than 200 divided by 3, so 66 and 2/3. And actually, since we know already that x needs to be less than 50, we don't need to worry about that. Okay, so that's the constraint on x. X has to be less than 50, but also x has to be a positive number here as well. Okay, so x also has to be positive. Okay, now in terms of, let's just consider b because I think it's the easier one. In terms of b as well can't be bigger than 100. In fact, it can't even be 100. Otherwise, these little boxes in the corners would disappear. So b has got to be less than 100, and again, b can't be negative. Now, likewise, on the other side for a, you can see that a also has to be less than 100. Because again, this total length is 200, and if we reduce down the size of x to nearly nothing, then we'll get two lots of a plus nearly nothing is 200. Now divide by the 2 and it will give us a is less than 100. So we can't have a being equal to 100 essentially, otherwise we'd have no room for x there. So a has to be less than 100. And we also know, in fact, that we've got a is the longer side. So we also know that a is bigger than b as well. So that's another constraint that we might need to deal with at some point as well. Okay, well, again, let's just check those ones. Let's see what constraints they're coming up with. So yeah, they're coming up with the same condition for x. X is less than 50. They're also mentioning that x is less than 66 and 2/3. And they're saying that a is greater than 0 and b is greater than 0. They're not putting on the constraint that a and b need to be less than 100. I think they really should do that. Okay, so part two is saying find the value of x which maximizes the volume of the box. Okay, so now here's the interesting bit. Just get rid of all of that. So those things, by the way, are just going to give us, in particular, our domain for x. Our domain for x there was up to 50. So on our graph, it's going to go up to 50 on the x-axis. Now we need an expression for our volume. An expression for our volume is going to be equal to obviously our length times our width times our height. So we're going to do x, that's the easy bit, and then times by a and times by b. And now we set up expressions for a and b. Now the expression for a was 200 take away 3x and divide by 2, and the expression for b was 100 take away 2x. Okay, take away 2x. Okay, and we can multiply those ones out, of course. We could multiply it out, or that might be a useful form as well. Perhaps just take out this half outside the front to start off with. So we've got x, half x, and 200 minus 3x, and 100 minus 2x there on the end as well. Okay, now this could also tell us where our turning points are as well, or sorry, where our roots are by setting these things equal to 0. So we can see we're getting a root at x is equal to 0. We're getting a root when this is equal to 0, which is at 50, and also at 66 and 2/3 from this one here. So the graph is going to go something like positive cubic. It's going to go through 0, it's going to go through 50, and later on it's going to go through 66 and 2/3. But that part is not going to be useful. So we're going to just be looking for the turning point up here. Okay, well, now it says find the value of x which maximizes the volume. So we're going to need to do dv dx. dv dx. So we need to differentiate this. Now, I don't know, I'm kind of reluctant to multiply that out. But if I don't multiply it out, I'm going to need to use the product rule twice. So the least thing I can do is multiply one of my sets of brackets out, so I can use my product rule once. But I think actually I probably best actually multiply this out. Okay, so I'm just going to cheat here to make things a little bit quicker for you. So here we go. This is our function here. So that's us multiplying it out. Again, that's just us multiplying these two things out. But from my point of view, I would take the half out to start off with. And you can see they're not showing you the steps there, but basically multiply out 100 minus 2x and 200 minus 3x, and then times the whole thing by a half x. It shouldn't take you too long, but you should end up with this expression here. Okay, once we've ended up with that, we can then obviously do dv dx. That's pretty straightforward. I'll do that one because that's easy. Minus 700x and then plus 1,000. And then obviously we're setting that equal to 0 and we're trying to solve it. Now, if you don't have access to a calculator, I'd probably go to, I'd probably at that stage think, okay, I'll use the quadratic formula because I'm not easily going to see how to factorize this. And, I can't see that 3 is a factor of all of this or 9 is a factor of all of this to make it simpler. Now, maybe it does factorize, in which case, great, but I'd probably use the quadratic formula in this case. Or if I have access to a calculator, I would obviously just find the polynomial roots in this case. Now, let's see what they're doing. Saying set it equal to 0. So there you go. You can see, in fact, you need to use the quadratic formula really there. And so they're coming up with two solutions. And, again, I'm going to steal a bit of this just to show you that setting that equal to 0 gives you these two solutions. So since x is less than 50, reject the second answer. And we know that, by the way, because, again, we knew where our roots were. Our roots were at 50 and 66 and 2/3. And we knew we had a root at 0 as well. So we knew it was a positive cubic. So again, it goes something like that. So that's what a positive cubic is looking like. But this whole thing is only valid in this domain here. Now found this coordinate point here. So we found the x value. And of course, we now need to work out the v value to find the v max. So the maximum turning point here. And we're going to do that by substituting this value stored on your calculator as a. And you're going to substitute that back into wherever the function was for v at the start. Okay, nice question. And I know questions like this have turned up in courses previously, and I know that a lot of people have struggled with those questions too. In fact, the mathematics is not too complicated here, but it's difficult to translate a real life problem into the mathematics to find the mathematics behind it. So it's difficult to set this whole thing up. That's the hard part of this question. Now, I can see as well that in the question they check the second derivative. You can check the second derivative if you want, but it depends what the question is really asking you to do. If it's saying show that this is a maximum turning point, then you're going to need to do that. And the most efficient way is to use the second derivative. But if you're not asked to show that, then I would simply know my shape of the cubic which comes out. I know it's a positive cubic, therefore I know the first turning point is going to be a maximum turning point. Okay, well there's the graph. And so that is done. Okay, 4R has a lot of questions there, so we've got 10 questions. They're worth doing. They're worth getting lots of practice with. They're quite difficult to set up. That's the main skill in these questions. And these might give you ideas as to where to go for an IA for your coursework. So be thinking about that as you're going through these questions. Now, there's 2 more questions there as well. So, they're going to be difficult to set up. And okay, so now they're going on to optimizing techniques using not the sort of technical manufacturing side of things, but we're talking now about the financial side of things, talking about optimization here through maximizing profits. Right, let's have a little look at the little graph that we've got here. Okay, let's steal this thing here. Oh, don't want to do that. Let's take this. Okay, so they're saying if you can come up with a total cost function and a total revenue function. So revenue is all the money you get in from selling your product, and your cost is just the total cost for selling this amount of product. And that might include fixed costs, for example. Maybe you've invested in some machinery to make your product, and before you've sold anything, you've still paid out for that machinery, and then you've got running costs and employment costs, which add to your variable costs. Now, if you take away these two things, you'll find out what your profit is. That is the total amount that you're getting in, take away your total cost. Okay, and that's now for any particular point of how many units we've sold. Maybe these are, I don't know, armchairs. Okay, 6 armchairs, 3 armchairs. You've got some fixed costs for these armchairs. Maybe that's all the wood that you've bought, that you've had to buy in bulk to start off with. Maybe maybe your tools have been given to you, and then well, you can see what we're talking about here. The profit is going to be the subtraction of those two things. Okay, now you can see that it doesn't make much sense if you've got fixed costs to sell a few units, because you're not going to make any money. You're not going to make any money until your total revenue hits your total costs. So you've got to be pretty sure that you're going to make 3 or more in order to be in the black, be making money here. Okay, and in this part we're in the red. We're losing money up until that point because we've not recouped the fixed costs which we had. Okay, so the loss is when we're doing this function, take away this function here, and we're saying, well, when the total revenue is higher than the total cost, that's when we're making a profit, and when the total cost is higher than the total revenue, then that's when we're making a loss. Okay, fairly obvious, but what you're going to need to do is make a profit function. Your profit function is going to be your revenue take away your costs, and then we're going to optimize for P in terms of the units sold, with respect to the units sold. Okay, so let's look at the question then. So we've got example 35 here. And again, I might not do all of the working out. Let's just see what we've got. So for example 35, says the cost of manufacturing fishing poles can be modeled by the function here, the cost, where X is the number of batches, each case containing 1,000 poles. So X represents one for X would represent 1,000 poles. The revenue is modeled by this function, again in terms of 1,000 poles, and a small company has enough workers to produce a maximum of 1,200 fishing poles. Okay, now state the domain of both the cost and revenue functions. Okay, well, now seeing as we have a maximum of 1,200 fishing poles, and seeing as this is in terms, the X is in terms of thousands of poles, then we have 1.2 thousand poles which we can produce as a maximum. And so that's going to be the domain for both the cost and the revenue function, because the cost and the revenue is both going to be seen as positive, because costs are going to be seen as a positive number when we're going to end up subtracting those two things. But as anywhere up until 1,200 poles, we're still going to get our answers for our costs and our revenues. But that's going to be the domain for both of these things. So in other words, it's going to be the same. It's going to be between 0 and 1.2. Okay, now it says find the number of fishing poles that the company should manufacture to maximize profits. Now, to maximize profits, we need a P of X, and that's going to be our revenue. So we're going to do X cubed minus 10X squared plus 20X minus this 7X plus 3. Okay, so now we're going to get X squared and minus 10X squared sorry, x cubed minus 10 x squared, that's minus 10x squared, and then it's plus 13x, and then it's minus 3 on the end. So there's our function for the profit. And now we need to maximize that. And now that's an easy problem for you to do. So I'm not going to take that further. This is now finding what is p dash of x and set it equal to 0. Okay, so that's that done. And then in the next part, it says the company introduces a new process that allows them to produce 6,000 poles. Okay, well, we've still got this function here, it seems. So it says find the number of poles that would cause the company to maximize profits or maximize losses. Now, the important thing here is that it's possible that you're getting this, obviously this x cubed graph. Maybe you're getting something like this coming out. I'm not sure where the top and the bottom are. Now, maybe up until 1.2, we had something like this. And, you know, there was our maximum point. And it might be that now we're extending to 6,000, that maximum turning point is no longer the highest point. It's quite possible that this point at the end is our maximum point. So we need to check our extrema. We need to check these extreme points of the function. So we're going to need to check the end point here as well. Okay, now I suspect that that's going to be higher than this in this question. So that's where you need to go for that one. Let's just have a little check. So x is equal to 5.94. So at x is 5.94, the profit is in an absolute minimum in its domain. Production level that would maximize losses is 5940. Oh, sorry, I've misread the question, haven't I? Because it says find the number of poles that would cause the company to minimize profits. Okay, so essentially we're talking about, and when we're getting this, you know, we're saying, well, we found this turning point here in our domain of 1.2. Now we're finding what's minimizing the profits. Now, again, we're going to have to check the other point over this side to see if this is actually lower than this in order to see if we're minimizing profits. And again, I kind of suspect that, in fact, this lower point is actually lower than this point at the end as well. But it's just really important to check the end points of this function. So have a little look. And for C, yeah, they're saying that to maximize losses, we're seeing that production level that would maximize losses is 5,940. We need to check, though, just that we should check there as well that on our function that we created, that when we're putting in x there, that you're not getting out a lower value. Okay, well, let's actually draw our function. Okay, so let's go to Desmos here. Check this, because we need to check these endpoints. Okay, that's taking a bit of time. So we have here y is equal to x cubed, and then take away, let's see what we're getting again. We're getting take away 10x squared, and then I think we had, what was it? So it was 20 and then minus the 7, and then minus the 3 on the end. So it's 13x and plus 13x, and it was minus the 3. So in the domain that we care about, that's between 0 and x and 6 now. If this is going to be our function, let's just plot this one out. Whoa, okay, so we can see we're getting a really big negative answer there. Okay, let's just zoom into this. So let's say the x-axis is equal to -1, and let's go up to 7, and let's go on the y-axis to, that's fine, okay. Maybe on the y-axis, let's just get rid of some of this bottom. Let's say that's going down to -100, and this is going up to, let's say, 30. There we go. So there we go, there's our function. And we can see that in our original, there we go, so take this. in our original domain, which was up to 1.2, so up to there, we can see that our profits are maximized here. Profits are there. Now we can see that if we make a ton of these things, then in fact our costs turn out to be really expensive if we're employing these other people. Maybe we need to train them or something. So we can see that if we extend our domain to 6,000 units, we can see that we have a minimum turning point here, and that's much lower than this value here. But we do need to check that that is lower than this one here as well. I'm not sure if the book has actually done that. So for part C, they really need to check the end point, okay, the start point. Okay, now when it's saying, for part D, it's saying by graphing the cost and revenue functions, find the number of poles that should be manufactured if the company is to break even. Well, that's pretty straightforward. That's just setting the two functions equal to each other and then solving a cubic equation. And again, we've got techniques of solving cubic equations, so I'm not going to go into that at the moment. But you can see that that's exactly what they've done. So they said break-even points are in two places there in our domain. Now, if we carried on beyond 6, you can see that there'd actually be a third place where this green graph crosses the purple graph there, but we don't need to consider that because it's not in our domain. Okay, now, so that's that done. By graphing these, so that's potentially, you want to do those using your GDC to find out the places where they cross. And then for part E, it says it would find, it says it would not maximize the company's profits to produce as many poles as workers are capable of producing. Use your graph to explain why. Well, that's this thing here. That's saying, well, as soon as we get past what's looking like 1.2 thousand units or 1,200 units, we end up going into a loss here. So this is saying we're losing more money here from this point here. So you just need a sensible comment on the end. What are they saying? They're saying the company's revenues decreases despite the costs continuing to increase. So this may be because of lack of demand for so many poles, which would mean they cannot sell them at all. Well, there we go. They're speculating at the end there, but essentially we're finding out from the graphs there. So the graphs which they've plotted, we've plotted a combination here for the profit graph, but they found out from the graphs that the costs, let's take this one again. Sorry to labor this, but they're saying that, you know, in this range that we care about up until 6, I think is there, our costs far outstrip our revenue. So our revenue decreases, in fact. I don't even know if that's realistic. You know, so our revenue is actually negative when we're producing 6,000 units, and I don't know why that is. I don't know if that makes sense or not, but obviously the costs are outstripping the revenue up until 6,000 units. Okay, well, there you go. There's the discussion on that one. And you've now got exercise 4S to do. There's lots of questions there. Obviously, get as much practice as possible. They're, again, good questions to do. They're questions which could lead you to thinking about a situation which you could develop for a piece of coursework. Okay, well, after 4S, we're dealing with kinematics, which we touched on briefly before. And that's going to be 4T. Thank you for listening, and hope to see you back next time.